Okay, so the main message that I wanted to convey yesterday I have never known if you have to put a hyphen there or not. I was putting it the other day in a paper, and the editor from the journal said no, it doesn't go. So I don't know if you guys know, but I got yelled at by the editor.
So you have to put a hyphen when it's a compound noun.
Oh, okay, so not here.
No.
Because it's not, yeah, okay.
So high energy theories.
There you have it.
Yes, but high energies.
That makes a little sense, yeah. Thanks. So was that, even though I'm writing the expression for the 4-point amplitude to go in, to come out, this is general for any number of particles or string states. But let me just keep writing it. As a function of just S and T, and if you remember, S plus T plus U is equal to the sum of all the, I'm sorry, in the case of 4 particles, this is sum of all the masses. Notice something that there's something really nice, or it's I don't know if nice, but it's just an observation that in the massless case, of course, this is equal to 0, but at high energies, what we're saying is that all of the Mandelstam variables are large compared to the string scale or any scale that you have in the theory. In this case, would be the string length. So for energies very large enough to that, this number is very big, so this is negligible. Okay. So okay. Okay, I will not say much about that.
So I have a question there.
Yeah.
Aren't you making the assumption that the center of mass momentum of the string is large, but that the level of the string is low? Because you can also have a high level, like you can have a lot of excitation, like you can have the state in a high level state. You can have the string in a high level state.
Yeah, I didn't want to get into that, but okay, since you already asked, let me just. So the spectrum, the string spectrum. I hope to answer your question. Let me know if I did not answer. Okay. So. So for the superstring, that is the string spectrum. For the bosonic string, this is there's a -1 or a -2 depending on whether you're a closed string or open string state. But for the bosonic, for the superstring, you have that. So what I'm saying is that in the high energy limit, which is basically, as we were saying yesterday, is when you take alpha prime to infinity. So all these states what am I saying? I'm sorry, I was thinking about the low energy. Yeah, okay, I don't think I'm answering your question then. No, what I wanted to say is that in the low energy limit, which is alpha prime going to 0, so all of the higher, all of the tower of the string states become infinitely massive, except the ground state, which is the massless graviton of the dilaton.
Yeah.
That one remains. So and that's one way you can see that why the low energy or the alpha prime going to 0 limit of the string theory, it's a field theory. Because all the massive states become exactly so they become infinite. So it's like you're integrating them out, but you're only left with the massless states. So it's a field theory at the end of the day.
Yeah, but here you have a large center of mass momentum. So if you imagine a string interaction, if you can transfer the energy from the center of mass to the actual excitation of the string modes, then you could, in principle, have enough energy to overcome the gap, unless you're taking outside the spectrum as well.
But you're right. Yeah. No, I'm taking the opposite limit now. Yes. Does that answer your question?
No. So okay. So then this relation between the Mandelstam variables will hold because the mass of the particle can be the mass due to the string excitation of the transverse mode.
Yeah, exactly. Yeah, no, you're right. Yeah, I was writing it. Yeah. Not right at the beginning.
Okay.
I was not conveying the correct message.
Okay.
I went to bed at 3 a.m.
No.
Listen. Okay. So, yeah. So what I wanted to say yesterday was that this comes. Let me be very schematic. Okay. So this is universal for pretty much any string theory. I mean, for sure you guys know that there are like 5 versions of the original string theory in 10 dimensions. There's the type 1, type 2A, type 2B, the periodic, and the E cross E8, E8 cross E8. So it's very general in the sense that in any of those theories, if you compute the 4-point amplitude at very high energies, whether it's closed strings, meaning gravitons and so on, or open strings, photons, gluons, or any other open string state, the behavior at high energy is pretty universal, and it has that form. And notice that here there's a power law, but that really doesn't matter in the high energy limit because also the exponential always, of course, wins in that case. Okay. So as we were saying yesterday, this is like a manifestation of why string theory is finite in the UV. It's not even renormalizable. I mean, it's not only renormalizable; it's finite, right? So it's even better than renormalizability. Now, this was tree level. What about 1 loop, 2 loops, 3 loops? So even again, I know many of you know these things already, but if you haven't heard of it, especially the students. In a string theory, let me say about the closed string for a moment. We have a diagrammatic expansion in the same way as we have a diagrammatic expansion in terms of loops, which also counts like the number of like the genus number. For example, for a graph in field theory, in string theory, you have the same kind of expansion, and it's pretty remarkable that. Contrary to the QFT case, where you have many diagrams per loop level, for the closed string, you have only 1 diagram per loop level. Okay, so that's kind of a neat thing also in string theory, that it organizes the loop expansion in a more in a simpler way. So the remarkable thing is that David Gross, and Paul Mende, in 1986, they computed this thing to any order, okay? And this what I showed was the tree level amplitude. A genus, this just gets modified by this simple factor over there. Okay. So they did a complete all loop computation. It's perturbative, of course. I mean, we're doing loop expansion. Whenever we say loop expansion, we are already saying that we're doing perturbation theory with respect to some complex constant. In this case, let me write it here, right here. This is called the string coupling constant that maybe you have heard that has to do with the expectation value of the dilaton field, and the dilaton field being the trace of the massless field that arises at the low energy limit of the ghost string spectrum.
Sorry, what is capital G? Sorry.
What is what?
Capital G.
The genus. So it counts, the number of handles, for example, in the Torah.
So it's a sum.
Sorry?
So the whole thing is a sum.
No, but this is not the full thing. This is for example, if you put g equals, I forgot how it starts, but if I give you g equals 1, it's one of these diagrams. If I give you g equals 2, is the next diagram, and so on. So you will have to solve, right? Okay. The full sum is the sum over OG.
That's what I said.
Yeah. But you see here I have g also, so let me just. So if you wanted to know, the 32 genus diagram at high energy is that answer.
So here, all the states are massless, right? So you are taking alpha to infinity. So
All the states are massless?
yeah, alpha is infinity, right?
Yeah.
So all the states are massless. The mn is equal to 0.
It's,
So you're
yeah.
neglecting n big n, right? So you can have n over alpha equal constant.
Yes.
This is not in the approximation.
What do you mean?
I mean, m squared is 0 or?
The actual limit that I'm taking is actually this. Alpha prime s. So I have to take a dimensionless number,
Yes.
large. So that is the one that I'm taking. And I'm also taking alpha prime t, much bigger than 1, but the ratio is fixed. Okay. And the ratio, since it's a function of the, if you remember yesterday we had this. Okay, yeah. And this also was like, if I remember correctly, was something like this. 1 minus cosine of theta. It was something like that.
Yeah.
Okay. So the ratio is just a function of the scattering angle. So
But I think
Yeah.
you have n there, n is equal to natural numbers at
Yeah.
0.
yes.
But you have big N, and you will have m finite, right? If you take n over alpha equal constant. So in
Yes.
this approximation, you are like taking everything is in the ground state of m equal to 0, or something like that.
I'm not sure I understand the question. So I'm not. This is why I put like quoted quotes here,
Oh, yeah.
because it's not the right way to take the limit, right? I mean, you usually find it written in this way, but what people really mean is this.
So no, maybe I get confused because of that way of thinking about it.
Yeah, my inattention. I'm sorry. Yeah.
No, okay.
This, but yeah. Okay. So. Let me just also give you like a quick. This is just to tease you a little bit with some extra stuff, which I think is kind of nice. So, I mean, very schematic. So at tree level, the topology of the tree level closed string amplitude, it was the sphere, and then at high order, at high group order, it's it's like a donut with many holes. So let me write it like a sphere with many holes also, and then you have vertex operators associated to the injection of momentum at different locations on that sphere with holes. Okay. If you remember a little bit from yesterday, when we had an amplitude, it was an integral over. Remember the positions of the vertex operators, and we could fix a few of them, 3 of them usually, well always 3 of them. And then you have to integrate over the remaining, variables. That integration or those variables are usually called the moduli in the string jargon. Okay? So when people talk about the moduli of the string theory, they refer to that. They refer to all these variables that you're integrating over in order to arrive at the string amplitude. So an endpoint amplitude is usually like an integral over many many of these variables. It's actually n minus 3 of them. And these are usually called the moduli. So it's just a fancy word to say you have a bunch of integration variables that you have to integrate over. And then you have here a function that depends on all the momenta. Okay, and okay, it's pretty much that. And when you take the alpha, when you take the high energy limit, what Gross and Mende noted that this integral here, you can approximate it using a saddle point approximation. The usual saddle point approximation that you learn in complex variables. And so I'm going to go into celestial holography right away. High energy. We can use a saddle point approximation. So, and as any saddle point approximation, when you do that approximation, that fixes locations on the integration range. Okay? So the saddle point equation is this. That is the saddle point equation. Okay. Now, what I want, so as a homework exercise for the students, check that this is actually SL2C invariant. Okay. So what is this saying? This is saying that you're integrating over a bunch of complex variables, but in the higher energy limit, that integral gets localized, around the saddle point. What is the saddle point? If you give me the external momenta, then you have to solve this equation over here, and then this will give you all the different values of z. But you have n possible z's. But if you notice, and if you use momentum conservation and the on-shell condition, you will find that this is SL2C invariant. Okay, so if you do an SL2C transformation, which is like that, as we were saying yesterday, for all of them, you will find that this saddle point equation is actually invariant. So that means that you can again choose 3 of this thing and get rid of them, and just focus on n minus 3, which is exactly the number that you have to integrate over here. Okay? It's just a nice thing that says that everything works out. Yes? You mean the full amplitude after integrating or before integrating? But this is an SL2C invariance over the variables you're integrating over. So at the end of the day, the amplitude is not going to depend on z, right? Because you're integrating over that. So this is like a property of the integrand, if you want to say that way. Okay. And if you guys have heard about this Cachaso-He-Yuan formula, anybody has heard this? Anybody? Okay. If not, okay, I'm not gonna say it. But there's a similarity with this, which is really nice, because this Cachaso-He-Yuan thing, which is from almost 10 years ago, they found a way of how to compute graviton amplitudes, which is the low energy limit of a string, and the same equation shows up there. But this equation shows up in the high energy limit of a string. So it could be maybe just a mathematical, universal thing, and because you have worksheet and things like that. But the high energy limit of a string and the low energy limit of a string theory seem to be connected through these equations. And there's still no satisfactory answer about why that is. Okay, it's a curiosity that that I just wanted to mention.
Okay. This is very similar to random matrix theory. This term.
Okay, I know nothing
It's
about
not.
random matrix. Yeah.
Maybe it's related. I don't know.
Could be.
And this is related to putting the propagators on shell or something like that when you're doing the sample.
Why are you thinking about propagators?
In an amplitude, when you put everything on shell, the propagator gets in the code.
You're sitting on a pole.
Yeah. It's the same thing or it's a different thing?
It has the same kind of form. Yeah. Yeah, in that case, when you're sitting on a pole, well, I have not written yet. Are you thinking about this? The PI that PJ goes like that?
Yeah.
Are you thinking about that? Yeah, but there's a big difference. This P and this Z's are independent things.
P is the external momentum.
It's external momentum. But it's not this. It's not when I talk about celestial holography, we're going to have something similar to this. But in that case, P and Z are just there's a one-to-one map. But here, P and Z's are completely different things. Because these Z's correspond to locations in space-time, whereas these Z's correspond to locations on the worksheet. So that's cool. Okay. All right. So this is what I want you to take home. Basically that formula, and I want to go now into the second title that. The second thing that I said that I was going to do. So, when yesterday I started with strings, then strings and high energy was the number one thing that I wanted to do, and the number two thing that I wanted to do about the high energy quantum gravity. It's what we put in the outline in the first lecture, which is called black hole nucleation. Okay. Okay. Okay, I'm going to go rather quick, but let me tell you references. Oh. Amati. There's more soldate also. Soldate. And also Giddings has many papers, but one of them is Giddings Porto from 2009. So I'm going to be, what I'm going to say here basically draws from the review that is in the first sections of that paper that includes, the previous literature and then some new stuff. Okay, and so it goes like this. I know this is going to be a little bit hard to believe at the beginning, so I'm going to write. This is what I want to compute. It's hard to believe because it raises many questions, but this is it's a very robust result based on many other people, but these are like the main authors, and in which you arrive at the same answer. In all that, you arrive at the same answer. And the one that the computation that I'm going to show is how black holes are created as intermediate state in a scattering process. Which is at high energies. Okay. So by high energy, we mean that the center of mass energy is it's not the Planck scale, but even larger than the Planck scale. So that is the limit that we're going to take. So if you read these papers, you're going to see that there's a very robust result in the sense that when you compute a scattering amplitude, here you have the propagation of a particle, or even bound states. You could propagate even bound states. Yeah. So what I wanted to say that it was hard to believe at the beginning was that you have creation of black holes also as intermediate states. These black holes, propagate in space-time, and then they annihilate into another pair of particles. So this is the scattering amplitude that I'm going to compute. 2 to 2, the usual one, but since it is at such high energies that the process that are going to dominate this amplitude is going to be the creation of black holes at intermediate states. Okay,
here,
that is.
Here, the black hole is like a bound state or something like that, or is a state, like a asymptotic state, or
No, it's not asymptotic.
okay.
Here's an intermediate state. You can think of it as a bound state also. But the picture is what we were saying yesterday. You have this. The center of mass energy is much larger than the Schwarzschild, or the scale of that energy is much larger than the Schwarzschild, or smaller than the Schwarzschild radius. So you create a black hole. Okay. Again, that sounds like too the chamuyo. Okay. But believe me that it's a very robust result.
But yeah, the reason is this: the center of mass is higher than the.
Right, but that sounds like hand waving, right? I mean, if you don't support it with actual computations, it's hard to believe, right?
Yeah.
But I'm saying that in all those papers and many others, references therein, you can see that the result, you arrive at the same result that I'm going to arrive now, that I'm going to show now from other types of computations. For example,
Out of ignorance, can I ask you a question?
Yeah.
Because it's really confusing.
I know.
No, but okay, so as far as I understand, the only thing that black holes can do is evaporate.
Yeah.
Yeah, okay, right. So let me just ask you a question.
So this is the
Yeah,
effect.
so the energies work out so that the evaporation time of the black hole is of the order of h bar over the center of mass momentum, over the center of mass energy.
Can you say it again?
That the evaporation, like the Hawking radiation evaporation time of the black hole is of the order of h bar over the energy of the center of mass. So it is basically you're in the uncertainty bound. Because then I can believe that you can consider it an intermediate state, like a virtual particle.
Yeah, I don't have a clear answer for that, but I think you're right. Yeah.
Okay.
Yeah. Okay. So let me just also give you like another hint for credibility for why this is. By the way, this is Veneziano, the same Veneziano. So the Toft did the same computation, but not using QFT pretty much at all, just using quantum mechanics or semi-classical. Yeah. Let me tell you what he did. So he modeled the. If I have a particle, another particle, they're going to smash together, and they're moving at very, very high energies, such that they could create a black hole. Then, of course, they will deform the space-time using the laws of GR, right? So, what is the metric that Transplanckian particles? What is the metric that they create? It's the shockwave metric, and this is called the Eichelburg-Sechsel metric. Okay, it's shockwave. There's a generalization of that which is called the PP wave, but it's basically that. Okay, so it's a shockwave. And then in this shockwave, the computation that Toft did was that if this shock wave have an impact parameter such that that impact parameter is less than the Planck length, then he showed that by using just GR, that there's a trough surface that it gets created. And that trough surfaces develops at horizon in a singularity. So that's your black hole. Okay. And then okay, he was not doing only GR, he was doing GR, but it was a scattering of high energy particles that obey the laws of quantum mechanics. So he obtained an amplitude for this process to occur. And that amplitude is the same result that I'm going to show you that these guys and other people also obtained using QFT. So in that sense, I want to motivate that this is actually correct. Okay. Now, of course, as usual, results or whatever as are as strong as their assumptions, and the assumptions here are there exists an S matrix. Okay, and the theory is unitary, which is a given in QFT. And also the computation obeys the usual rules of locality and causality and things like that. Okay, so these are like principles that it will be very hard for us to believe that they break down. They could break down. Maybe some of you will come up with that. A great theory of quantum gravity in which those principles are not obeyed. And this could be a different story. But that is what I wanted to say. And if you want to read more about what are all these assumptions that are going into all these are in this very nice paper and reviewed by Gibbons in Porto. Porto is Uruguayan, by the way. Okay. You guys know him, right? Yeah. Perfect. Okay. So let me go ahead and try to compute such a thing in a very schematic way. I'm not going to give all the details, but notice that. So these are usually called cutting rules in QFT, in which I can compute this amplitude by gluing together two amplitudes. This tree vertex with this other vertex, and then I put a propagator in between. Okay, that is, and the propagator is going to be a propagator associated to this black hole's intermediate states. Okay, so we need this. First, we need this kind of thing. For the center of mass energy of this interaction, I want it to be very large, Planckianly large, and so I'm going to produce one black hole, and that I is going to label some quantum index. Some quantum label. Okay. And why I'm saying that is, again, since this is a quantum mechanical process, I have to add up over all possible black holes, quantum states, which are called microstates usually, and I have to sum over all of them. So that summation is going to go from 1 to the number of microstates of a black hole. The number of microstates of a black hole is, in statistical mechanics, usually is e to the entropy, where the Boltzmann constant is equal to 1 in those units. So I'm going to have to use the black hole entropy, which is given by the Bekenstein-Hawking formula. And that simple fact that we have an exponential, that simple fact is going to give us that exponential over there. Okay, I gave you away the punchline of the whole computation. That's what I want to show. Okay, so first I need this one over here. Okay, so let me compute this process. So this process, I create a black hole. Let me call, as we said yesterday, we have an in state here. So and we have an out state here. Okay, so the first thing I want to compute is that amplitude over there. Okay, and let me give you the answer. Okay. Okay, that power law is not really relevant. This is what the relevant piece is. Okay. That exponential thing, and then
That's S over 2. S factor over 2.
yes, yes. And that is over the Bekenstein-Hawking entropy divided by that
Because
distribution.
the probability would be the amplitude square, right? So you
Yes,
can
yes, exactly. Okay, so so in units where Boltzmann constant, h bar, c are all equal to 1, but not G Newton because we want to keep track of G Newton because we're doing gravity. Okay, so that is the mass of the black hole. So that is the Bekenstein-Hawking entropy. And what we want, so what is we want to create a black hole. So the mass of the black hole is going to be given by the energy that we have available in the process. And what is the energy that we have in the process? Is the square root of S, the square root of Mandelstam S. Okay, so from now on, I'm going to write this as like that. Okay.
Francisco,
Uh-huh.
I don't know if you said that why is that like the probability proportional to the exponential of the
I'm going to give you the answer now.
okay.
Okay. Okay, this is just some phase. The amplitude is going to be a complex number, so there's going to be some phase involved, and the amplitude itself is going to be given by some polynomial function of the energy of the process. But the important thing is that this exponential here is going to show up in that amplitude. And as you can see, since we're in the high energy limit, again, this dominates, okay? Because it's an exponential suppression. Now, that answer over there shows the black hole creation is the dominating process in this scanner. Okay? And now I want to go and answer your question. So, we can see this as follows. I'm taking way too long. Okay. So, if I wanted to compute the probability for any of these in states to go into a black hole, then basically I'm going to square that amplitude, right? But I have to sum over all the possible intermediate states. So n is the number of black hole microstates. Okay. So as you can see, look at this. This is 1 to n. So let's just square this. Okay. So you're going to get e to the minus the entropy that 2 goes away, as you were saying, And that phase factor also goes away. That thing also becomes squared. Okay. And yeah, that's pretty much it. And now you see this thing just goes outside. Basically. And then I have the sum from 1 to n, which is just n. Okay. N. But what is n? And what is n? It's just the sum. But n counts the number of black hole microstates. So it's e to the Bekenstein-Hawking entropy. Okay, so this goes away, and this, let me just as an act of it's order 1 in terms of the energy. I mean, meaning that it's not exponentially suppressed. Okay, so what I'm saying is that, and I hope to answer your question now, Matthias, is that this form is the required form, the required exponential form that has to happen in order for black hole creation to be dominating the process. Okay, that is what I wanted to say about that. So let me continue here. All right. Okay, so as we said, we wanted to compute this thing over here, some in state, some out state. So this amplitude we computed this one over here. We computed kind of this process. Similarly, for that process, as you can see, it's basically very similar to that. So you're going to have also a similar formula for that. This process over here is going to be let me write it the way that I want to write it. So it's a consequence of time reversal actually, and it's going to have the same shape as before. E to the Bekenstein-Hawking entropy divided by 2. There's also some phase factor. Let me call it just replace it by this E to the some angle, and then find some function, some polynomial or some power law. So what we want to compute now is the full thing. So we wanted to compute so let me write it the other way around. In that goes into a black hole microstate. That black hole microstate then becomes an out state. That, and then I want to sum over all black hole microstates. So that is the thing that I want to do. Okay. So as you see, in this page. Okay, so that amplitude just by gluing the things that we had before was we had let me forget about, okay, this is just a power law. What I'm worried about is, I'm interested in the exponential factor. Okay, let me just forget that f function is not relevant. Okay. So we get that for the out one, and then for the in one, as okay, this is very trivial, but I'm gonna write it anyways. So we get that. So as you can see, I can take this out of that integral, and then I get 1n to the e to the I and I minus I. Okay? And now, and notice that it's very, very large. So even if you have a black hole of some normal scale black hole, then the entropy of that black hole is huge. And here we have e to that large number. So this is a humongous number. So it's a very big number. And these are just phases at the end of the day. So since they're just a bunch of numbers that go from 0 to 2 pi, let me call this some alpha. Okay. So this distributes. If you have a large enough number, distributes, and there's no particular value of this phase that is preferred. As a unit, so you can model it to be to distribute a uniform random variable. And a uniform distribution in the ranges of 0 to 2 pi. And then what I want to compute, since this is an amplitude, at the end of the day, I want to compute, the amplitude, the absolute value of the amplitude of the amplitude squared. But this is since I'm using some random variable distribution, and I would like to know how big this random variable is. What I'm going to compute is the usual thing that you do in statistics, right? I take the in order to see how big this number is, I'm going to take I'm going to square this thing. I'm going to take it basically the standard deviation, right? So I'm going to take the average of that, and then square. The average of okay. Okay. So let's do that. Let's do that. So what do we get? We get so basically, let me just focus on that part. So basically, we want okay. Maybe I'll just speed up. This is the usual random walk that you see in statistical mechanics. If you compute this thing with this number distributing uniform, it's a uniform distribution. This is going to go like the square root of n. Okay. Let me just. You can find it there's a cancellation. Whenever this thing is equal, whenever this thing is equal to 0, when you take the average, that is going to give you a bunch of 1s, and the rest are going to die out. Okay. And at the end of the day, you're going to have square root of n. So in this case, it's going to be e to the minus that divided by plus divided by 2. That 2 comes from that square root. Okay. I need to speed up. Okay, therefore you see right away that the amplitude goes like e to the minus SBH, e to the plus SBH divided by 2, and this gives an overall minus sign to dBH over 2. So this is e to the minus, what was it? I erased it. I think it was 2 pi gn S square. What was it? Yeah, S. Okay. So the function is, so the punchline is that where you see so when you include quantum gravitational effects in an amplitude and you go to extreme high energies, black hole creation dominates the process. And when black hole creation dominates the process, the amplitude is again exponentially damped at very high energies. And see, there were no strings whatsoever anywhere here. Okay? So quantum gravity, just because of the pure creation of black holes, and just because of that dominates at very high energies, the amplitude is exponentially suppressed in the UV, just like it happens in a string theory. So the main message that I wanted to convey, which is what we said yesterday, was that this might be a robust feature of quantum gravity, and string theory, since it's a theory of quantum gravity, that's why it reproduces this. Or if you're a hardcore string theory advocate, you can say that this is kind of it's because there's strings, going on somewhere in there. Okay, that was the main message that I wanted to convey. Okay. And now I move on to celestial holography.
You have 4 minutes.
4 minutes?
40.
40. Okay. Okay. So now, we've been talking about quantum gravity from the point of view of graphical amplitudes, or any amplitude in which gravity dominates, at both the low energy limit with the sub-theorems and the very high energy limit with this last results. And that was my excuse to introduce this topic of celestial holography, because it mixes. So it mixes the deep IR with the deep UV in a way that CFD structure naturally appears. When studying amplitudes, okay? Okay. Okay, so for the ones who know ADS-CFT, the holographic quantity, let me just be very schematic. So this is time. Okay, this is the bot, and this is a boundary. So usually, ADS is drawn in this using these diagrams, and ADS-CFT says that there's a duality between a gravitational theory living in the bulk. It's completely dual. So all of the physics that you can extract from that gravitational bulk theory in a certain number of dimensions is the same as the theory that lives on the boundary with 1 dimension less than the bulk. And that theory that lives on the boundary is a conformal field theory. But celestial holography is an attempt to holographic theory that involves gravity also, but in asymptotically flat space. So instead of being asymptotically de Sitter space and anti-de Sitter space, we want to do it in asymptotically flat space. So how many of the students are familiar with Penrose diagrams? Okay. So you may know more than me for sure. Penrose diagram. So the Penrose diagram let me do what's called the let me do something similar to that. So this is the Penrose diagram of Minkowski space. So this boundary here, as opposed to the boundary of ADS, this is a null boundary. This is a null boundary. Okay. So things that happen here in the bulk, we also want to do the same thing. We also want to do like a mapping between the physics and the bulk of physical observables that you can compute in the bulk. We want to compute them in terms of a theory living on the function. Okay? And there are some indications that the theory is some kind of deformed CFT, but it does not have all of the traditional features of a CFT. Namely, for example, it looks non-unitary, but that non-unitary has nothing to do with the unitarity in the bulk. Okay, the theory in the bulk is unitary, and this thing is mapping to a description of a CFT, which it could also be unitary in the sense of a CFT, but it has some aspects that it doesn't look like the usual CFT, and people are calling that celestial CFT. That's why there's this CCFT over there. Okay. So let me just get rid of that extra dimension over there. So so this is the Penrose diagram again of Minkowski space. This line is r equals to 0. This line here is r equals to infinity. R equals to infinity. But also, not only that, it's a null line. Okay. And what we want to do is we want to do scattering. For example, if I shoot a bunch of gravitons or a bunch of gravitons, I prepare this. So gravitons, since they're massless, they emerge from the past null infinity. And whatever comes out, photons, also gravitons like that, which are massless, arrive also at null, but future infinity. Okay. So if I wanted to compute a scattering amplitude, then my in state is defined here, the out state is defined over there, and I can compute an amplitude. I can compute an amplitude again, as we were saying yesterday. There's an S matrix that evolves the in state into through the whatever happens here, and then evolve it all the way up to future null infinity, and that is the amplitude that I want to compute. So this object over here, okay, encodes all of the physics that happened in the bulk, and what we want, and this is what celestial holography does, or celestial amplitudes. They map this object here, which is defined in the 3+1 bot. So as a bunch of operators, and it becomes a correlation function of operators that live on the 2D celestial sphere. Okay. This is just introduction. I'm going to be more specific now. So the basic idea the basic idea is that if you had a scattering amplitude, you can do a transformation on it that it becomes a correlation function defined on the 2D celestial sphere. So yeah. There's a whole other avenue for flat space holography that goes under the name of Carolian holography. And Carolian holography maps these correlation functions in 4 space-time dimensions to a three-dimensional boundary. Okay, so in that three-dimensional boundary, so here, yeah, okay, that three-dimensional boundary has has one more coordinate, and that coordinate is it's what's called the null time. So, by the way, I'm going to introduce that very quickly.
In the future infinity has 3 dimensions, codimension 1.
Huh?
The null surface, the future infinity is codimension 1.
Okay.
It has 3 dimensions.
I agree. So,
Right, so there is one further dimensional reduction that you haven't specified there.
exactly. So that third dimension actually gets mapped to a conformal dimension in that object over there.
Right.
I'm going to. So in a sense, it's kind of similar to ADS-CFT in the sense that the radial direction becomes like an energy scale for the CFT.
Right.
In this sense, it's also here the null time direction becomes a conformal dimension of that correlation.
Right.
In practice, the non-null direction is treated totally different than space-like time-like direction.
Say it again?
Null-like directions.
Yes.
We treat it completely different from time-like and space-like.
Yes. I agree. Yes.
So, because the metric basically looks like if we were not d minus 1, but d minus 2.
Yes.
That's it.
But what is it? What is the question? I mean, it's two
No,
ways
the question
of writing the same thing.
No, the question is, in ADS-CFT, one is more or less used equal something, and you project directly into infinity, and you get an effective d minus 1 metric.
Yes.
If you do this here, you will get effectively that d minus 2 dimensions. That's always confusing.
No, you're right. You get when you project it, you get a d minus 1 metric as well. Okay. As he was saying, the null boundary, yeah, it's a three-dimensional manifold.
Okay. Sure.
But no, you're right. Yeah. So, in the sense of the metric, I agree with you that it's going to be just a three-dimensional manifold, and you're going to have 3 coordinates: the 2 angles, azimuthal in the other angle, and the null time, u or v if you use this Bondi.
Yeah, but the metric will be non-partial.
What?
The metric will be non-impartial because it's not a space-time. It's just
I agree.
light
It's a
space.
light thing. Yeah.
So you don't have length along one of the directions.
You don't have what?
Length.
I agree. Yes, you don't have. Yes, you're right. No, it's a very delicate thing. Yeah, I agree. For example, I know that Marquenot and other people, Hernan, for example, they're working on the Hamiltonian formalism, which is weird, right? Because it's like the Hamiltonian is the generator for time translations. So here it would be like a Hamiltonian for translations along null time. But Marquenot, for example, he claims that things can be worked out in a similar way as in the usual Hamiltonian formalism.
Yes, I believe.
Yeah, that's fun. He's the one who invented the Hamiltonian formalism, basically. Yeah. Okay. And so I agree. So in this other things called Carolian theories, what you have there is a correlation function that lives in 3-dimensional space with these 2 angles and the null. But the celestial, what's called the celestial amplitude, you integrate over basically what's the energy, and what you get at the end is you get just a 2-dimensional. So you get a 2-dimensional manifold, which is just a sphere, And the extra coordinate, because you're integrating over that, gets mapped into, this. It's like a Fourier transform, right?
Yeah.
Okay, so as in ADS CFT, this zero order check for the duality is the matching of the symmetries, right? So the ADS, the group of isometries of ADS 5, for example, is the same as the group of the conformal group in one dimension less, right? So that is the. So you might wonder, okay, so what is that zero order test in terms of symmetries? So what are you going to get? I mean, we have just scattering in flat Minkowski space. The only thing you have is the Lorentz group. So this is the matching. Okay, there's a nice isomorphism between. So this is usually called also the Lorentz group because of the isomorphism between Lorentz transformation and SO 1,3 and the group of global conformal transformations on a sphere. Okay, so there are many ways to see this. I'm going to show you a way which is not the most straightforward way to see it, but it's very clear from the point of view of a space-time. From a space-time. Okay. So it's so whenever you're dealing with null surfaces in flat space, a very useful set of coordinates is they're called the boundary coordinates. Okay. So or U, sometimes it's U. Or U, sorry. So U is T minus R, V is T plus R. Okay. And depending on which, if you're at future null infinity or a past null infinity, for example here, if you're a future null infinity, then T is very large positive, R is also a very large positive, so this difference can be finite. And when you're in past null infinity, you use this coordinate here because T goes to minus infinity and this goes to plus infinity, so you can have a difference that you can make finite. Okay, so that is, so you use U for this one and you use T for V for that one over there. And also, instead of using the usual Cartesian coordinates or the spherical coordinates for the two angles, we're going to use complex coordinates. Use also so here I will try to be a little bit more pedagogical. So. So X, Y, and Z, and R, it's also next up there. But if you want to go back to spherical coordinates, you can write this as that. Where theta and phi is just the usual spherical coordinates. Okay, so now you can ask the following question. So if I do a Lorentz transformation, for example, in the bulk, okay. But what if I do it using this coordinates over here, this boundary coordinates, okay? So let me do it for Z, for example. I'm just going to pick one of these coordinates. So it's going to be Z prime, and Okay, so what is z prime? Well, you have to already transform each of these. So x1 prime plus I x2 prime divided by r prime plus x3 prime. And each of these are going to transform with this ugly matrix. So this is going to give you, you know, a huge thing. So this is something nasty divided by something also which is nasty. Another nasty here. But the nice thing is now you expand in powers of 1 over r. So you take the r here, because I want to see how these Lorentz transformations in the bulk, how they become, you know, how they look like when you look at null infinity. And so I'm going to take r going to infinity, and what you get, you get here a bunch of constants, which is going to involve like a linear combination of different, you know, components of this Lorentz matrix here times z, plus another bunch of constants divided by another bunch of constants times z, plus another bunch of constants like that, and then you're gonna get 1 over r corrections. Okay, and you see, and because of this mapping has to be invertible, that you need to require that be equal to some finite number. So you require it to be not different, different from 0, and you normalize it to 1. You can always choose that, and then you get exactly here the group of SL2C transformations. Okay, so it's not the most straightforward way. You could I'm only here doing the R infinity expansion, but it's a nice way to see how the conformal group just has the information about all the global conformal group on the two-dimensional sphere. It's basically the manifestation of Lorentz transformations in 3+1 dimensional space.
Is there a reason to get AD minus BC plus 1? So
say it again?
Is there a reason to get that condition? AD minus BC plus
You mean the one, or you mean the finite?
the final?
The finite is if you do an SL2C transformation, you need that to be finite in order for this transformation to be invertible. To be invertible. To be like a, you go back to the same. You know, to be bijective in mathematics. So if that is equal to 0, you see that you can see that z is become a constant.
A, B, C, and D don't depend on R.
Yeah,
Don't.
they don't. Right? There are just a bunch of numbers of the Lorentz transformation. Right? So all the R dependencies. Okay. So that's one nice way to see the global conformal group in 2 dimensions appearing from the Lorentz group. So then what we have basically is that yeah. So this is very schematic. It's not intended to be exactly like this. But for example, you have let me do this cartoon. I have a scattering amplitude of something going on here. There's for example some Feynman diagram, whatever, something going on, and then things come out. Okay. So the scattering process involves injecting momentum. This sphere is at infinity. right? And this is what astronomers have called for, for a very long time, the celestial sphere, right? It's the sphere in which, the light rays, pierce the sky everywhere. So a scattering process, you imagine it as momenta being injected, on the sky. Something happens here, and then the result of that scattering also becomes momentum injection at some point in the celestial sphere. So what we're saying is that the whole problem of celestial holography is to associate an operator here. Since this is a two-dimensional thing, and as we said earlier, this z-coordinate zi, so it was e to the I, it was tangent, right? Yeah, tangent of so I just labels the particle that is being scattered. So that z really represents piercing the celestial sphere at some point at infinity. So I'm going to associate. I want to associate an operator. To the locations of each of this injection of momenta on the celestial sphere. So as you can see, it looks similar to what we do in string theory. In string theory, we also compute scattering amplitudes, and we associate an operator injected at some point on the world sheet. But here we have operators injected on some point in the celestial sphere. Okay? So many people think that, I include myself, that there might be a relationship between string, when you study string amplitudes in the bulk, in Minkowski space, there should be a mapping, or there might be a mapping between the injection of these vertex operators on the worldsheet and this injection of vertex operators on the celestial sphere. Yeah, but okay. I'm advertising myself, so I don't want to say that. That's kind of the one of the hopes. Okay, so how one? I have said a bunch of things, but how? So let's get to work. How does this mapping, or how is this mapping? Really computed. Okay, so you start in the bulk. In the bulk, you start with an amplitude that depends on n momenta, and what we want is to rewrite it as a correlation function on. So this lives in 3 plus 1. These momenta are defined in 3 plus 1, and these z's are defined in 2D, right? So this is 4D Minkowski, and this is 2D Euclidean. Right? So it's an Euclidean. So yeah. All right. So until what? 10 minutes. Okay. I'll try to wrap up. So the first thing is, what is this mapping between the momenta and z? And this is a nice representation that you can use. So I'm going to write this 4 momenta in 4 components. The 4 components. Okay, so you can check. That 2 things. You can check that pi squared is identically equal to 0 for any value of z. So this gives you that this parameterization of the form momentum. It's a parameterization for all massless particles in any direction. So I'm going to be focusing on massless scattering because we're doing graviton scattering. Then this is perfect in that sense. And also check that if you remember yesterday when we were defining the Mandelstam variables, it was the momentum 1 or the momentum 2 or the momentum 3 and 4, whatever, squared with a minus sign. So this is the generalization of the Mandelstam variables for n-point particles. Okay. So these are the Mandelstams, and you can check that this is equal to omega I, omega j, zij, Cij bar, where Zij is Zi minus Zj. Okay? So notice one thing. Notice just flashing things, okay? So notice, for example, that sometimes when you have a Feynman diagram, for example, at just the tree level, there's a propagator here. And that propagator usually goes like 1 over, if this is Pi and this is Bj, Pi plus Bj squared, plus the mass of the intermediate state that it's going there, right? Plus I epsilon, the I epsilon prescription that I'm forgetting about right now. Okay. So since we're doing, for example, if we're just doing graviton scattering, then this is equal to 0. Right? There's only gravitons in the spectrum that is equal to 0. So notice that this becomes 1 over omega I, omega j, Cij squared. Right? This is Cij squared. So you right away see in this parameterization something that people know for a very long time. That when you have a propagator corresponding to a massless state, you can have a divergence coming from two different origins. You can have a soft divergence, and by soft divergence meaning that if the energy of the intermediate, if the energy of one of these external particles is very small, it's very soft, so that omega I or omega j goes to 0. Remember that omega is the one that parameterizes the energy. And this only has information about the angles, all the energy dependencies in that omega. So if either of these incoming particles has soft energy, it's very, very soft, you're going to have a divergence. And these are called infrared divergences in any scattering amplitude. Or if they have finite energy, there's nothing wrong with their energy, but if the particles are going collinear, right? No. If the particles are going collinear, that means that this Cij is going to 0. And again, you have a divergence here. So this parameterization is very useful in order to parameterize soft divergence or collinear divergence in just in a very simple way. Yeah, okay. And ¿cuánto me queda? Sí, correcto. So, yeah. Since I ran out of time, in CFT language, this thing's called the operator product expansions, which have to do, for example, when you have correlation functions. Let me do it in 2D. If you have a correlation function, and you take the limit when, for example, one of these two go collinear or not collinear, but you don't call it collinear in CFT. You call it, they become, coincident. then this usually can be written as a summation of that. Yeah, some power here and some operators here, or some operators here that okay, I'm being very schematic. I'm sorry about that. But the objective of the operator product expansion is that you can understand the singularity that occurs when those 2 points go coincident as like poles times some other operators which are finite when those coincide. So those coefficients here have all the information about this singularity. Okay, that's what the OPE is about. So notice that since in celestial holography we're doing that, we're going to have these collinear singularities. So real collinear singularities in the bottom, when particles go along the same direction, they produce singularities. In this language, they become like OPE expansions of the CFD. So there's a vast literature since 5 years now about how to relate celestial holography. So there's a vast literature in relating collinear physics with OPEs in CFD2. Okay. That too is because of the two-dimensional CFD. All right. Okay. Is my time up or?
You can still have 1 minute.
5 minutes?
But maybe they don't want to. Yeah? Okay. You always have 5 minutes.
It's a tongue translation in the statement.
I have a question.
Yes.
So, is something similar to the amplitude is similar to the an amplitude computed in strings, right?
Yes.
But you still remember something is crucial to be in the critical dimension. And why here we don't have problems with that? Perhaps we are only considering 3 levels.
Okay, so from the point of view of the worksheet CFT, the critical dimension is critical in order to conserve conformal invariance, right? At the quantum level. Here,
We're missing 22 dimensions.
ah,
We're missing 22 dimensions.
can we defer the question for like after I finish? I mean, it's a very good question. I don't have a clear answer right now, but yeah, it's just after.
Unitarity in the previous one, but unitarity for the matrix how translated to that.
That's an open question. Still, it's an open question. Yeah.
So I have a question about the collinear divergence, because here you're mapping a collinear divergence into a UV divergence, because basically in the OP limit.
I mean, it's Euclidean, so UV it has to be taken with a grain of salt.
That is true. But basically, like in a CFD, when you have this in the OP limit is basically small distances, right? So this is like a UV divergence modulo the fact that here you're in a Euclidean CFD.
Yes.
Right. So, but in the case of the coincident divergence, just like in the case of the soft divergences, like the IR soft divergences, the prescription that particle physics teaches us to take care of this into account is to take into account detector physics. So basically, to say that the detectors have a threshold in the energy resolution that you can measure, and in the spatial resolution in which they can detect the particle.
Yeah.
So this is sort of like let's say ad hoc physics, like physically motivated.
Yeah, many people think that it's okay.
Which works very well.
Not always.
Well, I mean, for a specific detector, they do, right? So here,
And for a specific scattering process, people know how to take care.
Yeah.
Yes. People know how to take care of these things.
Yeah.
Not even for n particle process. It's
Right.
when it goes from 2 to 3, 3 to 4, and sometimes you have to include initial radiation. Sometimes you have to include outgoing radiation in order for these divergences to go away. But it's extremely ad hoc.
Right. This is true. Right. So then this is my question. Like, what would be the analog physically motivated prescription to regulate the UV divergences that you're inducing in your celestial sphere? Because unlike the case of the coincident or collinear divergences you have in a standard field theory, you don't have the detector physics to take into account to regulate this divergence.
So you're saying, okay, we have like a ad hoc where we have some answer to
Yes.
deal with collinear divergences in the bulk.
Yes.
And since
But
they
what
map
is- yeah,
to
exactly.
UV divergences,
Yeah.
how you treat
Yeah,
those?
because UV divergence is an entirely different beast. So I understand that here you are in a CFT, so technically you have a QFT at the conformal fixed point. So your beta functions are seated already at the fixed point. So it doesn't make sense to talk about the renormalization, which is the usual way that you actually deal with UV divergences, right? But then what would be the analog of the ad hoc way that you deal with the collinear divergences in the bulk in standard physics? Because you're claiming that this is map, right? And so then I'm asking you, how do the solutions map as well? Like the resolutions to the problems map?
Yeah, that's a very good question. But it's two different things, right? Because from the point of view of the collinear divergences in particle physics, the resolution is just some technological thing.
Yes, but it actually does take into account the divergences by a process analog to smearing. Essentially, you're smearing on the scales of the detector.
But you can say the same thing here, right? This collinear divergence is also like
Right, so it's like you would need to introduce some smearing in the separation scale of the
Right, but-
something like this.
But
But I ask you, how is it taken into account, like in the computations?
well, let me ask you, how is it taken into account in the original computation?
From the point of view of particle physics.
Right.
I think they actually smear this out over some detector function, like a field.
Then why cannot you? Yeah, I don't know the answer. I don't have a clear answer also. But I'm not sure if it's a well posed question, in the sense that. So you're asking me for a theoretical resolution of a problem which is on the other side. It's not even theoretically solved.
No. Because I mean, you can take like actual scattering processes of massless particles. Let's say, some scattering of some graviton or some.
You mean, yeah, okay. They do the actual computation,
Yeah.
and they know how
Yeah.
to deal with the
Yes.
how to get rid of the divergence.
Yes.
How does that map into this language?
Yes.
Okay, yeah, that's a good question. I don't know if anybody has worked on it. I don't think nobody has worked on it.
Okay.
So yeah, sounds like a good project.
Right. And the other question that I have, well, it is related to the question that was previously asked. So basically, you're saying that this same idea of vertex operator insertions in the 2D CFT, that it's the same sort of techniques that are used when dealing with the worldsheet computations in string theory. So, but you also said yesterday, right, that this is just a feature of the state operator correspondence in CFTs. So maybe I don't know if it has a deeper meaning, right? Because you're saying that to you, the fact that you can use the same techniques somehow points to the celestial sphere structure in the celestial sphere, which is actually physical space. It is the two-dimensional transverse space of the Minkowski-Edwards diagram, right? Edwards diagram. So that this points to some string theory, but maybe you answered the question yourself that this is just because of the fact that if you have a CFT, then you can kind of always do this creation. Because if you really wanted to see this coming from a string theory, you would need basically that the wordsheet of the string should only be in the two-dimensional transfer section. So basically, for some reason, the string shouldn't be wrapping around any of the compact dimensions. So
Oh, you're saying like the full sphere is also the wordsheet? I have like a.
it would be. I mean, it's the only way, because if not, the string would wrap some of the compact dimensions.
Yeah. Yeah.
Right. So you would need some mechanism as to why the string cannot wrap any of the compact dimensions.
But here you're mapping, you're mapping the wordsheet into the full celestial sphere. I mean,
Right. So I mean, the wordsheet. I agree that there is a difference between the wordsheet and the target space.
Yeah.
But you can have a situation where the wordsheet is entirely on certain two directions in the target space, which is what you did here. So you
Right.
need that the two dimensions of the wordsheet can only exist in the two dimensions of the transverse section of the target space, and not wrapping around any of the extra compact dimensions. This is okay, but why would this happen?
I don't know.
Uh-huh.
Sorry, but where is the target?
I mean, here the celestial sphere is the target space.
It's part of the target space. It is the transverse section in the Minkowski diagram of Minkowski 4. Yeah.
I would say more than this a mapping rather than the celestial sphere is the actual wordsheet.
Right, but then the mapping is a mapping between CFTs.
Yeah.
The fact that you have a 2D, so the fact that you have a 2D CFT means that you're inheriting all this property.
Yes.
It doesn't need to have a string geometry.
Yeah, I agree. Yeah.
Okay.
Yeah, I agree.
Okay. Right, thank you.
Now we are
Yeah. I finished. I guess already. So. Yeah.